Look at the modern archetype of eco-friendly architecture. We see vertical forests, glistening solar arrays, and lobbies lined with top-tier sustainability plaques. The global construction market is pouring trillions of dollars into these designs, promising a clean, green future. But despite the greenery and the gold-plated certifications, there is a widening gap between what these buildings promise and what the environment actually needs. We are constructing buildings that appear sustainable, yet contribute directly to ecological collapse. This happens because our metrics are built on a comparison to the past, rather than the physical limits of the future. The entire construction sector evaluates itself using relative progress. They ask if a design is better than an arbitrary standard baseline, ignoring the absolute physical reality of the planet's carrying capacity. This chart shows how traditional life cycle assessments operate. These assessments are the foundation of major green certifications, and they are inherently comparative. They evaluate performance by setting up a highly inefficient standard building in red and rewarding a design if it produces a slightly shorter green bar. The gap to zero remains massive. Because developers only need to beat this relative baseline, the system encourages point chasing. Designers will often install automated water sensors or complex control valves to score efficiency credits. Yet those specific devices draw continuous electrical power, creating parasitic loads that can actually make the building consume more energy overall. Meanwhile, these models often downplay the massive surge of emissions that happens before anyone even moves in. The extraction and production of materials like concrete, steel, and glass require an immense amount of upfront energy. This timeline illustrates what researchers call a carbon debt. When a highly efficient new building is completed, it starts its life deep in the red. It typically takes 10 to 15 years of daily operational energy savings just to offset the carbon emitted to build the structure in the first place. And those projected energy savings assume the building operates perfectly forever. In reality, mechanical systems age and solar panels experience dynamic degradation, losing roughly 0.5% of their efficiency every single year. Buildings rarely meet the pristine targets simulated during their design phase. Our certification systems are engineered to reward projects for being less bad, rather than verifying if they are actually good enough to keep the environment stable. To fix this, scientists are adopting absolute environmental sustainability assessments. Instead of comparing one building to another, this method measures impacts against planetary boundaries, the hard, physical thresholds that define a safe operating space for humanity. Applying this global limit to a single project requires a process called downscaling. Researchers take the Earth's total remaining environmental budget and mathematically allocate a tiny fraction of it to represent the maximum allowable impact for one single-family home. This 2019 Aalborg University study applied this exact method. They analyzed 5 experimental mini CO2 houses built in Denmark, utilizing cutting-edge strategies like upcycled materials and maintenance-free components. Even under highly optimistic renewable energy projections, not one of these 5 houses achieved absolute sustainability. Every house overshot its assigned ecological limits by factors of 11 to 42 times. The heavy upfront carbon footprint required to produce their durable, energy-intensive materials far outweighed the savings from their daily use. This data suggests that under our current industrial paradigm, a truly sustainable new building simply does not exist. Incremental adjustments to standard construction cannot bridge a gap of this magnitude. This graph demonstrates the law of diminishing returns in building design. As you add thicker insulation, you reach a threshold where the carbon cost of manufacturing that extra material eventually outweighs any operational energy it will save over its lifetime. The industry often suggests replacing concrete and steel with bio-based materials like mass timber. While wood does sequester carbon, scaling this up to meet the demands of global construction introduces severe trade-offs, shifting the environmental burden directly onto land use change and ecosystem degradation. We are hitting the hard limits of technological optimization. To achieve sustainability, we have to adopt the principle of material sufficiency. We need to physically reduce the absolute volume of new construction, rather than just changing the ingredients of the concrete. The building sector must shift its entire mindset from innovation by addition to innovation by subtraction. The most effective action we can take today is a retrofit-first mandate. By repairing and adapting existing structures, we preserve the heavy structural frames and envelopes that represent the highest material masses, cutting the upfront carbon debt of a project by 50 to 75%. Reusing existing foundations and masonry bypasses the massive upfront carbon debt associated with pouring new concrete and forging new steel. Every existing building is a stockpile of already spent emissions. When new construction is absolutely necessary, it must follow design for disassembly. This treats structures as modular material banks held together by reversible connections, allowing components to be unbolted and reused later rather than demolished and sent to a landfill. It is a transition to a circular architecture. We must recognize that we do not own the materials we build with. We borrow them from the earth, arrange them temporarily, and must ensure they can be returned or continuously cycled. Rewarding buildings for being slightly less destructive won't save the climate. True sustainability exists only when designs respect the absolute physical boundaries of the planet.